G'day there. You're watching the Aussie BIM Guru, and today we're covering a fairly advanced and interesting topic in Revit, and that is projecting Revit floors onto a topography using Dynamo. This is quite a common workflow, especially when looking at paving on top of an existing topo surface or tin surface from a survey, and hopefully it will be a useful workflow. So today I'll be using Autodesk Revit 2022 and Dynamo for Revit, of course, and I'll also be using a custom node from DataShapes, a ray bounce node, and I'll also be using a element sketch collector from Spring Nodes. So you will need those packages as well, or the ability to create these outcomes using Python yourself. It is assumed you'll have some fundamental knowledge of Revit floors and topography, as well as just some basic Dynamo knowledge. So you can follow along with some of the actions I'm doing within Dynamo and also some of the geometry processing techniques that we'll be using along the way. So without further ado, we'll jump in, and of course if you find I'm talking a little bit too fast or slow, feel free to change the speed of the video. Some people often say I talk too fast, so hopefully slowing down the video helps those people. Definitely appreciate not everyone speaks English as their first language, so that's mainly why I put this here. But without further ado, let's jump in. Alright, so this is just a testing model just to show the principle of what we're doing today. But the goal is we're going to project this floor onto the topography. One step will be looking at the boundary points and projecting those, but then we're going to look at projecting an internal grid of points to make it more closely match the topography as well. We're just going to deal with one floor for this workflow, but you could build this script in a way that works with multiple floors at the same time. I actually prefer to make this work on a single floor at once because then the user focuses on reviewing the output one floor at a time, and it's much safer than them running it across the model and ignoring errors that might happen. But let's get started. So I'm just going to work with this topography, which has some points defined in it. It's a very simple topography. And then I'm going to be working with this floor that's a little bit more complicated, and it has quite a complex sketch. It contains some NURB lines and also some straight lines, so it's fairly complex. It can sit above or below the floor. We're going to work with a process that tries to get it really far up in the air so that it can project back down onto the topography. Okay, so I'm just going to go to Dynamo, and we're just going to be beginning, of course, with our floor as our logical first element to deal with. So I'm going to make a new script. I'm just going to save this, and I'll just call this floors to topo. So I'm going to begin by selecting a model element. And I'm going to select my floor in this case. I'm then going to be doing a few things with this. So I'm probably going to try to get into Dynamo and sort of out of Revit pretty early. I'm going to be using springs, and I'm going to be using the collect sketch. I think it's called the sketch, collect sketch or something like that. Collect element sketch. And this will enable me to ask my floor for its outlines, and I can basically switch over to Dynamo at this point because I have sort of a visual preview of what we should be dealing with here, which is these outline curves. So now that I have these, I can sort of visually deal with them. So we're just going to be dealing first of all with dividing these outline curves into a set number of points, and then we can project those at the topography, and then we'll have a look at the internal grid afterwards. So to begin with, it's going to give us a set of curves, I should say. I'm going to flatten this list. So currently we'll sometimes have multiple lists depending if you have holes in your floors or if your floor is comprised of multiple sketch objects. I can see now I just have a list of curves and NURBS curves, and I'm going to try and divide these by a max spacing. So I'm going to go and grab a length node, and I'm looking for the length of this curve. So we'll use curve.length, and then I should be able to divide this by my target spacing. So let's for now say that my target spacing for these points is going to be a number, and we'll just say for now 150 millimeters, and that will give me a decimal number. Sometimes it might happen to be a whole number, but generally you're probably going to be dealing with decimals. So what we're going to do with this is round up. So I'm going to use a math.ceiling node, which will force these all to round up so that we're dealing with a maximum spacing we can allow. From here, I'm going to be generating sequences based on these numbers of points. So I'm going to go from 0 to 1 with n as the number of spacings between them. And this will give me a set of sequences with the number of objects in there corresponding to the number of divisions that we need to create our max spacing. So this is a shorthand. It's actually a shorthand for the sequence node. So I'm dealing with the start, I'm actually dealing with a range, I should say here. A start, an end, and a step, but instead we're dealing with a number of objects we're trying to create between those start and end numbers. So it's just a shorthand code block. And with this, I can create points at those parameters on those curves, because I've created in this case basically a list of points between 0 and 1, which is the domain of a curve. So with these parameters to these curves, you can see I'm now dividing these objects. Now, this isn't quite equally divided. One challenge with NURBS curves is that their domain is not always equally spaced when you're dealing with parameters. You might also be able to potentially deal with the segment lengths instead. So what I could do here instead, I think I could do point at segment length. Yes. And I'm pretty sure we could use a rolling sum. Instead, it's a little bit more complicated. So for this, I might potentially just use Python. So what we'll do instead is we'll go from 0 to L, the maximum length. And this will instead give me a list dealing with the length of the curve. So I'll just take these sublists and we'll go into Python. And I'm just going to be doing a rolling sum for each list in here. I don't believe there's a node by default that does this. So I'm just going to be using Python, so I don't really need anything in this piece of Python. But I'm just going to say for now that my rolling lists is going to be an empty list. I'm then going to say that my in list is going to be in 0, so the first object we're collecting in the Python scripts. And then I'm going to say for in list in lists. So for each list of values, I'm going to say that I start at 0. That's the first thing I would begin with at the very start of the curve. I can then say that my rolling list is an empty list. I can then say for value in list, and I can begin probably just by firstly adding the value onto the start value. So I'll actually say this is current value. I'll say CURVAL current value. And I'm going to say current value, and I'm going to use the plus equal syntax. So this is going to raise this by the value, and we'll always be beginning with adding 0, so you will just begin with a 0, but from there this sum is going to keep climbing. So at this point I can then say that to the rolling list we would like to append the current value at that point. So this is going to keep adding it onto the sum each time. So instead of individual values, we're going to be collecting the sum progressively. Once I've finished with that, to rolling lists, I'm going to want to append the rolling list that I just generated. And finally, I can say that out is rolling lists. And this should generate a rolling list instead. And we can see that's working. So we can see instead of 403, we actually get the result of adding 403 on instead. So we're getting a much more suitable outcome. And I believe with NURBS curves, this should give a much more even distribution. So that might help a little bit here. Okay, something not quite working. Geometry scale. I might need to, in this case, say that we're using these segment lengths for this curve. Yeah, it's still not happy. Okay, something hasn't quite worked here. 403, 4032, 600. I'm wondering if this doesn't deal with... Maybe this does deal with progressive lengths. Oh, it does. Okay, never mind. Ignore that Python, but there's a Python technique anyway. Now we can see it still doesn't really... It's a little bit more even than before, actually. I think it looks better. So probably point at segment length is a better technique. Now if I can also create a slider here or just adjust the value. So you can see that I can do less or more points around the edge. And these are going to be the points that we project onto the topography. So the more points you add, obviously the more precise your projection will be, but the more heavy and slow the process will be, and also the floor that you create in Revit. So for now, I'll just stick with 150. I'll just leave this in here as a little optional Python block, but it turns out we don't actually really need it. So nice little technique anyway. So now that we have these points, I'm going to flatten them and just get all the unique points around this curve. So I want to use the prune duplicates node here. And I'll just leave the tolerance as default. Now we should get rid of any common points at the corners. So we have 4 corners, so we'd expect to have 4 less points, and we can see that has worked. We went from 67 points to 63. So now I can just go back and do a little bit of cleanup. Probably just turn off a majority of the previews that I don't need. So in this case, I really only need one particular node to see the curves. So in this case, I might just keep the flatten on, and I might just keep the prune duplicates on for the points. So at this point, we have the ability to pretty much project these onto the topography. But what we're going to do first is actually, I'm just trying to think what the easiest way to do this is. We're probably going to deconstruct these points and then set their Z value to a very high value to get them far above the topography. So I might do this using a code block. And I'm going to be making points by coordinates. Now the coordinates I'm going to be dealing with here are going to be the X and the Y coordinate. So I'm going to say P.X, P.Y, and then Z in this case is just going to be a fairly arbitrary high number. So for now I'll just say 999, 999. It's quite high. I can now take these points and put them quite high above here. So when we project them down at the topography, we should be fairly confident we're going to hit topography, even if the floor was underneath the topography originally. So I might just need to go and now just enable geometry scaling. So under preferences, visual settings, you might have this, sorry, it's under general in this case in 2022. I'm just going to work with extra large for my units, and that should get rid of that warning. Okay, so the next thing we're going to want to do is do a ray bounce. So in data shapes, there should be a ray bounce node, and I find this is better than the default ray bounce. I'm going to probably do on a linked category, I think. So in this case, this works with points, a direction, a 3D view, so you will need to be in a 3D view to run this, a category that you're targeting, and a setting whether you would like to just bounce on links. In this case, I will say false. So I'm just going to, first of all, give the points. For the direction, I'm going to take a Z vector and I'm going to reverse it. So I'm going to reverse the vector so we're pointing down. I'm also going to take the current view. You could take the first 3D view in the model as an alternative approach if you really want to make sure that someone's always going to be in a 3D view. But in this case, I'll just make it that you have to be in the 3D view. I should now be able to provide the category of topography. And I'll also say that we don't just want to bounce on links. I'm now just going to turn off the preview for my really, really high points and zoom back into my, well, I might not be able to zoom back into it. It seems like it's not going to be happy with that. Thanks, Dynamo, really useful. Might just turn off the preview and see if that, no, it's still very, very high. Okay. I do find sometimes Dynamo does really struggle in focusing on objects. There we go. I think if you select one from a preview list, it works. So at this point, we should have points that should be generated when we hit the topography, if they hit the topography, of course. So I can just double check this just by probably just checking these points. I'll just call this preview, and this will show us those points. So we can see now these points are following the topography. So I can see in 3D, in Revit, that these are successfully finding the topography along the edges of that floor. So now that I've done this, the last thing that I need to do is add these to the floor as points. So from Dynamo, I'm going to look for the add point node, and this is going to be add point to point shape, and we're looking for the floor-based one. Now I'm just going to switch to manual mode for now. We're going to go back and get our floor. I'm then going to just sort of straighten that pathway out, and we're adding these points to that floor. So let's see what happens when we hit run. And there we go. We can see this floor has now successfully elevated itself onto the topography along its borders. So what this has done is modified the slab subshape and has elevated the points to the necessary height relative to the floor in order to reach that point. So you may want to move the floors to a better height that is a good relative reference before you run the script sometimes. So maybe you want the floor to be on the datum so that all the elevations are based on relative levels. But in this case, we can see that this has successfully found the topo. Now, what if this topography needs a little bit more resolution in the floor? Notice how we're sort of clipping under and over the topography, depending on where we are. Let's maybe try to overlay a 3D point grid in addition to the edge points. That will really help us, I think, better match the topography. So I'm just going to, for now, just freeze this node, and I'm also going to reset the slab shape. And I might just switch to wireframe for now. So we're going to go back all the way to where we had our floor, and I'm going to be using the extent of the floor to assess a 3D equally spaced point over the top of the floor, and then we're going to add the points that would intersect the floor if they were shooting down towards it into the points that we're adding onto the topography. So I'm going to, in this case, need a bounding box, and in this case it's going to be an element based bounding box. So somewhere in here there should be a bounding box by element. Here it is. And for the floor, we want its bounding box, and this is going to be axis aligned. We're going to take the minimum and the maximum point. So there should be a minimum point and a max point node. So I'm going to put minimum above and max below. There's those points. If you ever want to see the bounding box, you can use the bounding box to cuboid node to give you an idea of the box that we're currently working with, and there it is. It's quite small because the floor, of course, is currently flat. But what I'm going to do is now reconstruct this box at a fairly high height above the ground. So I'm actually going to probably reconstruct these points using a code block. So I'm firstly going to create 4 points, P1, P2, P3, and P4. And these will be the corners of the rectangle that we can use to generate some lines in order to assess where a point grid would sit over the top of this box. So I'm going to say that P1 is equal to point by coordinates. I'm going to say the minimum. Whoop. Now I could use the surface at the top of the box as well. There's a lot of ways you could do this step. I'm just trying to work with the most primitive geometry I can. And we'll say 999, 999. We'll go quite high again. So in this case, I'm going to be firstly doing the bottom corner of the box. So the minimum X and Y coordinate would be that point, the bottom left corner of the box. I'm then just going to copy this 3 times and make these new lines and call these P1, P2, P3, and P4. The next one would be the minimum X and the maximum Y, then the maximum X and the maximum Y, and finally the maximum X and the minimum Y. I'll take my minimum and my max point. I can go back to running an automatic now. I would say that's fine. And we'll now have these 4 points available. Now they are going to be quite high in space. So what I might do is actually just make a variable for the Z value. And we're going to keep it temporarily low, and then we'll raise it up at the end to make sure we're sitting above the topography. Now, if you want to be absolutely sure you're above the topography, you could also take the bounding box of the topography, or the topography you're dealing with, and try to make sure that you're going to be above all of those objects, but it's a more computationally intense process than just specifying an arbitrary, fairly high number. So it's up to you whether you want to work more absolutely. So for now, let's just say we want to work at 2 meters. We're going to sit a little bit above the topography, but we can see now we have these 4 points sitting above the topography around its extent in the bounding box aspect. So I'm going to turn off the preview for the actual bounding box, and now we're just going to deal with these elevated points. So I'm going to need to do a few things here. I'm firstly going to need to construct both an X side and a Y side for the box so I can assess them. So I'm going to make a line by start point, end point. First of all, I'm going to take the bottom left corner, and I'm going to be connecting that to the top left corner. So this is going to be the Y side of my bounding box, or the frame that I'm building. I'm also going to be taking, in this case, the lowest left corner, and finally the furthest or bottom right corner. So I can use these curves to assess the length in both directions of the point grid that would need to overarch this floor from above, in order to overlay a point grid onto it. I'm now just going to be doing, and again, another assessment of the length. So I'm going to do a curve length. In fact, I might just borrow some nodes from before. I'm really just targeting these nodes here. So I'm just going to, in this case, borrow this. And I'm saying I want the curve length divided by, in this case, a secondary spacing. Now let's make this a little bit bigger, maybe 300. There's going to be quite a lot of points generated if we make this too small. So again, we're dividing this by the ceiling. In this case, we're actually going to be doing this a little bit differently. I believe we're going to go from 0 to 1. And again, n in this case is going to be our ceiling. So we're going back to our old method, but I can see now roughly how many things I would need. I would need 1, 2, 3, 4, 5 divisions or points along this edge in order to create a roughly evenly spaced grid atop the floor. So I'm basically just going to be borrowing this again. Now I am going to create another range, and in this case I'm going to go from 0 to 1, and I'll call this one N2. So we're also going to be targeting our X direction as well as our Y direction. And now I can see I have an X range, and now I also have a Y range. Our X range is obviously much wider, so we're going to have more points or divisions along here. But we're going to basically be using these to assess a rectangle that is going to represent this space. So what I've built there is effectively an X and a Y grid for assessing the parameters in two directions upon a surface. So I'm going to make a rectangle by corner points 1, 2, 3, 4. In this case, I'll take point 1, point 2, point 3, and point 4. And we now have a rectangle around here. And then I'm going to patch this into a surface by using the surface by patch node. And we can assess this surface in both the U and the V direction, which we will. So I'm just going to move this over here because we're going to use both our X and our Y grid of points as our U and our V assessment. So I'm going to go point at parameter on surface, and on this surface, our U direction is going to be our X direction, and our V direction is going to be our Y direction. And we also need to work with a cross product so that we're working with every combination of those two. And we can see what we've just done is created a 3D grid of points that we can overlay onto this floor. So maybe in this case, let's just make this a little bit smaller, maybe 200, or we'll just go to 150 for now. And you can see as you go smaller, you're going to create a roughly square grid of points that we can then also shoot down at the floor in our ray bounce. Now, firstly, we need to find out which of these points actually are inside the floor. Because if they're not, obviously we're going to have a problem, right? So what we're going to do here instead is we're going to get our actual floor as a surface. So I'm going to, in this case, I'm going to make an assumption that my floor is just going to be a single closed floor, but you could deal with other ways of assessing the geometry of the floor. If it has holes in it, if it has multiple loops, there's other ways you could assess if these are actually in the floor. In fact, maybe, I'm wondering if I could do this more easily. I think for now, I'll keep it simple. I'm just going to take my floor boundary, and I'm going to use a polycurve by joined curves. Now, obviously, this isn't going to work for every single type of floor, but for now, just as a simple example, I'll combine all these curves into a single polycurve and patch them. But there are other things you could do here to assess whether the points are going to hit the floor itself. You could potentially use another ray bounce, assuming there's no other floors around your floor in the X and the Y direction. Or you could request the floor's solid geometry and process that instead as an intersecting form. That would be another option. For now, I'm just going to deal with this patch though, just to keep it simple as an example. And I should now have a patch. I don't believe I need to flatten this list. I think it's going to come with just a single surface. Just in case it doesn't, you can also use list flatten if there's more than one surface there. For now, I'm just going to turn off that preview and also this preview. And we're going to be checking if a line drawn down at the floor intersects this. So what I'm going to do at this point is I'm going to create a line, but I'm going to move these things back up quite high. So I'm just going to put these back at 999,999. I'm going to copy that value. Now at this point, we don't really want to see any of these things. They're a long way above our model now. So we're just going to turn off all their previews. And and just turn this off. But what we're now going to do with these points we've just created is shoot them down as a line and see if they intersect the floor. So I'm going to go by start point, direction, and length. So I'm going to make a line by start point, direction, length at those start points in the negative or the reverse direction of the Z vector, so down. We're going to make curves, and these are going to be to the length of that number that we've moved them up by, just back in the other direction, so that times -2. And these should come right back at our floor. And I might potentially just flatten these as well. So before I actually get those points, I'm going to flatten that list. And I'm just going to turn off these previews. Now we don't seem to be able to see these lines at the moment. They're definitely there. So I'm not sure why we can't. Of course, we don't want to reverse the vector because now we're just going down using the maths. There we go. So there's our points being shot back down at our floor. And we're just going to ask these lines if they intersect the floor's geometry. So I'm going to do a intersect, and I'm just going to check if these intersect. Now, in this case, we just want to take the intersection result because we have a surface and the line, and the result of intersecting those should be a point if they do intersect. So I'm going to take my surface, and I'm also going to take my lines, and I'm just going to work at the longest lacing, and we should get all the points that do successfully hit. In this case, some of these will form an empty list of intersections. That's fine. I'm going to flatten this list, which should both put these all down to one level and also clean out any empty lists in this case. But we can see now we have an even grid along our floor that is going to overlay itself as points within the floor. Now, sometimes we might want to include this grid, sometimes we might not want to. So we're going to use a if function to do this. I'm just going to use Python to do this part. And we'll need 3 inputs. I'm going to have a boolean. And actually, we don't need 3 inputs. We just need 2. So I'm going to say, in this case, include point grid. And we'll say when it's false, we send through nothing. When it's true, we send through the point grid. So I'm going to put these through like this. And I might just turn off the previews as I go now, because we know that's there in the background. And it's a very simple output. In this case, I'm going to say, I'll say if input 0, which is this true? And if it is, then we want the output to be the second input, the points. Otherwise, we want the output to be an empty list. We want it to be nothing. So at the moment we can see we have nothing, then once I set this to true, we don't. Now you could go back a step and go all the way back to this point and just provide nothing there, an empty bounding box, or you could negate one of these inputs so that all those calculations with the rays hitting the surface don't have to be run. So you could potentially save yourself a little bit of computation time there. You could also, in this case, instead just set this number to something very large in an if output to say, if we do that, we only want to get the absolute corner points, which we know typically shouldn't intersect the floor. And in that case, you could also make this like a really large number, like 999,999, because in that case, you just won't end up with many divisions at all. You'll end up with basically 1 division, which would be very few divisions to calculate as array. But for now, we're just going to put it right at the end, just to keep the logic really easily understood. What we're going to need to do now is sort of intervene around about here. So I'm going to move this further down, and we're going to want to add these points in before we shoot them way up higher to run our intersection. So what I'm going to do here is create a join node, and we're going to join these points onto these points. Sometimes you'll have them, sometimes you won't. But now instead, assuming we set this to true, we can see we also have the ability to project the extra points onto the topography as well to create that overlaid point grid. So this will allow us to much more closely hug the geometry of our topography. So with these points, I'll go back to manual mode, unfreeze the final node, and I'll just go to hidden line instead. And just to keep things simple, I'll turn off some previews just so we don't see too much. And I'll hit run. And we can see now that we'll project our floor, but we're also going to overlay a secondary point grid. And you'll notice that we much more closely hug our topography with the floor now, because we're taking additional calculations in between the boundaries of the floor. This becomes really necessary when you're dealing with very large and wide floors over topography, where really the boundary of the floor isn't enough to reflect how it sits on the topography. So really, you'd want to use boundaries only really when you're comfortable with the output you'll get. Usually for really narrow paths, it's okay, but for very large topographies, you usually want to include an internalized point grid. But we can see effectively we created a very quick and useful tool, so I can go and create pretty much any floor of any shape. I can go and set that floor. And then by running this tool, I can very quickly project that floor onto a topography with a very tight fit, depending on the internal point grid that I wish to overlay. And we can see that, a human would not easily be able to do this. That's a lot of manual calculations that would have to be made visually, typically. But Dynamo can very quickly and easily help us make this projection using Dynamo. So I hope you've enjoyed this. So there we have it, quite a useful script, and you can find a copy over on my GitHub with a sample model if you found it a little bit too hard to follow along or you're just curious to see how the script works at surface value. So I hope you find that useful. So if you're not already following and subscribing, feel free to do so. If you've got any comments or requests, feel free to leave them down below as well, or you can drop me an email if you need, also at the address on this screen. So feel free to like, comment, share, all that stuff. And I look forward to seeing you in future similar videos. Thanks. Take care. Bye.